Hello everyone, I'm Dunit from Event Driven Utopia. In this video, I'm going to talk about message queues in detail. Let's start with the fundamentals and see what are the available messaging styles in message queues. After that, let's see what are the features common to message queues. Then let's discuss why do you need a message queue in your architecture. We'll explore some advanced scenarios and wrap up. What is a queue? A queue is a data structure that mimics a real-world queue, like this one. A queue has two ends, the front end and the rear end. Items are added from the rear end, and this is called the end-queue operation. Items are removed from the front end. This is called the dequeue operation. A queue is a first in, first out data structure. That means the first item added to the queue will be the first one to be removed. A message queue is a queue of messages. Messages are stored on the queue until they are processed and deleted. Now let's look at a typical messaging infrastructure. A messaging system consists of producers, consumers, and the message queue itself. Producers produce messages and store them on the queue. Consumers retrieve messages from the message queue and process them. Producers and consumers can be different application components, like web applications, microservices, that need to communicate with each other. Messages carry the information that is meant to exchange. For example, it can be something like an e-commerce order, a user's registration, and so on. Any number of producers can send messages to the same queue. But the queue guarantees that each message is processed by a single consumer. There are ways that a message is processed by many consumers. Let's talk about that shortly. Now let's look at the life cycle of a message from its origin to the end. The journey of a message starts from the producer and ends at the consumer. First, the producer sends a message to the queue. Consumer may or may not be available to consume the message at this time. So the queue keeps the message until the consumer is available. When a consumer is ready to process the message, it consumes the message from the queue. But the queue does not delete the message immediately. It stays there until consumer completes the processing. In the meantime, the queue temporarily locks the message to prevent the same message being consumed by another consumer. After processing, the consumer deletes the message from the queue to prevent the message from being consumed again by another consumer. Distributed applications typically use message queues to implement one or more of the following basic message exchange patterns: one-way messaging, request-response messaging, and broadcast messaging. Let's look at the first one, one-way messaging, also known as the point-to-point messaging style. The producer simply sends a message to the queue in the expectation that the consumer will retrieve it and process it at some point. Consumer polls the queue for new messages and ultimately receives. Request-response messaging, also known as the RPC style. The producer sends a message to a queue and expects a response from the consumer. If the response is not delivered within a reasonable interval, the producer can either send the message again or handle the situation as a timeout or a failure. This pattern usually requires a separate communications channel in the form of a dedicated message queue to which the consumer can send its response messages. The producer listens for a response on this queue. Broadcast messaging, also known as pub-sub messaging or push messaging. The producer sends a message to a queue and multiple consumers can read a copy of the message. In this case, consumers do not compete for messages. This can be used to notify consumers that an event has occurred of which they should all be aware and may be used to implement a publisher-subscriber model. Let's try to understand this with an example. In this diagram, a topic acts like a queue to which the producers can send messages that include metadata in the form of attributes. Each consumer can create a subscription for the topic, specifying a filter that examines the values of message attributes. Any messages sent to the topic with attribute values that match the filter are automatically forwarded to the subscription. A consumer retrieves messages from a subscription in a similar way to a queue. In this video, I'll be talking mostly about one-way messaging pattern. Let's look at the other two in a future video. Many message queue implementations share a common set of features. Let's explore them in detail. At least once delivery. Once you put a message to a message queue, its infrastructure makes sure that the message is not lost. A message queue is a distributed system made of multiple servers. Each server is called a broker. Once a message is received, the message queue redundantly stores the message across multiple brokers for durability. This architecture enables at least once delivery guarantee for the messages that are sent to the queue. Exactly once processing. There's a possibility for a producer to send the same message twice. For example, a producer might crash after sending a message but before completing any other work it was performing. Another producer will replace the original producer and it could repeat the message. So the queue will have duplicate messages. Some business use cases will be affected if the same message is processed more than once. For example, consider an e-commerce application processing orders. The same order can't be charged twice in that case. Most message queues has built-in support for duplicate message detection and removal. This is based on the message IDs and known as deduping. This makes sure each message is delivered to its consumer exactly once, and most importantly, only once. Ideally, the message processing logic should be idempotent so that if the work performed is repeated, this repetition does not change the state of the system. Message ordering. Some solutions may require that messages are processed in a specific order. For example, financial services and e-commerce customers, and to those who use messages to update database tables. Message queues provide best effort ordering, which ensures that messages are delivered in the same order as they are sent. Most message queues offer two flavors for message ordering. Standard queues. The order of messages may not be guaranteed in standard queues, but they offer a high throughput. If you have a high throughput messaging need that doesn't care for the order of messages, go for standard queues. FIFO queues, or first in first out queues. Messages are delivered in the order in which they are sent, but there's a trade-off. They offer a limited throughput. Choose FIFO queues if you care about the message delivery order. A message queue can play a critical role in your application architecture and can be beneficial in many ways. A message queue enables reliably exchanging messages among application components. Even though consumers fail, the queue will deliver the message to another consumer. A queue makes sure that a message is consumed by only one consumer. When a message is being consumed by a consumer, the queue puts a lock on the message so that other consumers can consume it. This lock, however, has a time limit. If the consumer fails to delete the message during the lock period, the lock will time out and the queue lets other consumers to consume it. If a consumer fails while processing a message, the queue will release its lock on the message so that another consumer can retrieve it and process it. Now the message is back in the queue again and ready to be consumed. Likewise, a message queue always ensures that the message is processed at least once. With a message queue, producers and consumers do not need to communicate with each other directly. Also, it allows different parts of a system to communicate and process operations asynchronously. A message queue provides a temporal decoupling. That means producer and consumer don't have to run concurrently or at the same time. A producer can send a message to the message queue regardless of the availability of the consumer. Conversely, the consumer isn't restricted by the producer's availability. Also, the message queue operations are asynchronous by nature. After sending a message, the producer shouldn't have to wait until the consumer completes it. This makes the producer responsive and it can immediately go back to its caller. Also, producers and consumers can go offline for maintenance tasks. They can be upgraded independently because they don't know about each other. Adding new producers and consumers to a queue is straightforward and makes less impact on the application architecture. A message queue helps to scale your application by distributing the load across multiple consumers. Also, it will act as a buffer to smooth any spikes in the traffic. Let's look at that in detail. You can use a message queue to distribute processing across consumers and improve the overall throughput. For example, producers may post a large number of requests to a queue that is serviced by many consumers. Consumers can be added dynamically to scale out the system if the queue length grows, and they can be removed when the queue has drained. Consumers can run on different servers to spread the load. The completing consumer pattern explains how to process multiple messages concurrently to optimize throughput, to improve scalability and availability, and to balance the workload. A message queue can protect consumers from sudden bursts of messages sent by multiple producers. Instead of adding consumers to handle this work, a message queue acts as a buffer, and consumers gradually drain messages at their own pace without stressing the overall system. For example, if your consumer is slow, you can use a message queue to buffer the incoming traffic so that the consumer continues processing messages with its own pace. A message queue can be used as an application integration hub as well. Message queues enable integrating components running on different platforms and that are built by using different programming languages and technologies. Based on the use case, you may implement an appropriate producer or consumer that conforms to a message format agreed upon. This will open the doors to many opportunities, including legacy application modernization, hybrid cloud integrations, and so on. There are some advanced use cases associated with message queue implementations. It is important to know them when designing and building systems that are based on the message queues. The dead letter queue. Message queues have a special queue called dead letter queue to hold messages that couldn't be delivered or processed. The message queue itself or any consumer can put messages to the dead letter queue. For example, a consumer can put a message into dead letter queue if it fails to process the message after several attempts. The dead letter queue keeps the message until they are retrieved from the queue, which is a manual operation most of the time. Message expiration or time-bound message processing. A message might have a limited lifetime, and if it is not processed within this period of time, it might no longer be relevant and should be discarded. In this example, the message must be processed within 2 hours. Otherwise, it should be expired and discarded. Usually, message queues put expired messages into the dead letter queue. Message scheduling. A message will be visible on the message queue only after a specific date and time. The message should not be available to a consumer until this time. In this example, message will be invisible for a time period set by the producer, so consumers can't see the message. When that time period elapses, the message will be ready for the consumption. Poison messages. A poison message is a message that cannot be handled because it is malformed or contains unexpected information. A consumer processing the message could throw an exception and fail, causing the message to be returned to the queue for another consumer to handle. The new consumer will follow the same logic, fails the processing, and returns the message back to the queue. This cycle could continue indefinitely and obstructs the processing of other valid messages in the queue. Hence, it is important to detect and discard them as early as possible. Generally, poison messages are put into the dead letter queue as early as possible. Priority messaging. A message can be assigned a priority to determine where in the queue the message is added, to make sure that higher priority message get bumped to the front of the line and processed first. In this example, producer assigns a priority level 1 to the message so that it will end up in the front end of the queue by circumventing the messages with low priority. Alright, we've been discussing a lot about message queues. As a developer or an architect, you will have to deal with a message queue at least for once in your lifetime. So let's try to recap what we have discussed today. Choose a message queue if you are building an application that needs a guaranteed end-to-end delivery of messages. with its redundant architecture and reliable message handling mechanism. A message queue makes sure that once you put a message into that, it will reach the destination under any circumstances. This makes a message queue an excellent choice for handling high-value business messages, like financial transactions. If your application architecture evolves over the time, introduce a message queue to promote indirection, loose coupling, and asynchrony. A message queue decouples workloads, so message producers and consumers know a little or nothing about each other. This will be greatly beneficial when you want to add new components to your existing architecture in the future with a very less impact. Choose between throughput versus message ordering on a case-by-case basis. Sometimes you don't need a first-in, first-out queue. There are many message queue implementations in the market to choose from. Choose the one that best fit your needs. Don't go after the hype. In fact, there's a great diversity in the market, starting from Apache ActiveMQ, RabbitMQ, and Kafka. Also, there are cloud-native products such as Amazon SQS, Azure Service Bus, Nets as well. Each has its own specialties and limitations, and there's no silver bullet in the messaging market. Thanks for watching the video, guys. We'll see you in another video.